The name of the first speaker is Stephen Ray from Indiana University in Bloomington, United States. I know Stephen, I would say, since so many years that I would say I know him since the beginning. And these are the scientific specialities of Stephen. He was working in fluorescence spectroscopy, development of novel sources, in particular ion sources, development of sample introduction systems for atomic spectroscopy, and development of time-of-flight instrumentation for plasma ion sources. And most recently he started to work with a very novel development of a new instrumentation which is given the name time-of-distance spectrometry. And now we are coming to the first presentation. Stephen will give a presentation about the versatile flow discharge and will show us new applications in atomic and molecular spectrometry. Stephen, the floor is yours.
Good morning, and Zhao Xing Hao. Did I get that right? Yeah. All right. I want to thank Norbert for the wonderful introduction that he gave. I don't know how he found all those photos of me as a young child. And I'd like to thank the organizers for the opportunity to be a part of this wonderful symposium. It really is an honor to be included with all these wonderful speakers that you hear about today. Celebrating the 25th anniversary of the Journal of Analytical Atomic Spectrometry. And in many ways, JAAS is really the preeminent journal in our field because it's a home to many atomic spectroscopists within the community, whether they're doing LIBS or doing atomic absorption or atomic fluorescence spectroscopy. And I would just echo the words of May and Nia in saying that it's important in two ways. One is that it's a very respected international journal, a place to publish your work. And while we don't publish every paper that we put out in JAAS, we certainly consider it as one of the premier sites to publish a lot of our results. And secondly, it's part of the atomic spectroscopy community. And I mean community in the best sense of the word. The idea that there's a group of people that in many instances are centered around JAAS that care about promoting atomic spectroscopy and ensuring that it has a very bright future. And I know a large part of that future is in this room here today. So with that as a background, I simply want to start talking a little bit about one of the sources that we work with in Gary Hika's group at Indiana University, and that is the low discharge. I'm going to talk about three examples that we've developed in our laboratory where we'll be looking at a solid, liquid analysis, and finally a gaseous analysis to get both atomic and molecular kinds of information. So let's start first with what's the traditional application of low discharge. And of course, everybody knows that it's typically used as a direct solid samples analysis because it really is simple and it's direct and it's cheap and it's easy. You can take a steel sample and place it in a glow discharge instrument and get an idea of what the bulk and the trace components are with really good accuracy. And of course, in atomic terms, that means we have to think about things like high sensitivity or multi-elemental analysis, stable over a very wide dynamic range. But I'm really interested in highlighting the one at the bottom here, the idea that we can get depth resolution now from the surface of the sample going down through successive layers on the order of nanometers per second, which is very important for a lot of applications that are in, say, the photosynthetic type of industry or semiconductor industry, if you're doing paint layers and things like that. Now in our laboratory, we really want to add another bullet point here. We'd like to be able to say that glow discharge also has lateral spatial resolution. In addition to going through depths of layer, we'd like to say that you can get a good idea of what might be on the X and Y axis there. But the final goal of maybe making a three-dimensional model of what the surface looks like. A lot like what you would get with SIMS or something like that, but doing so a lot more cheaply and with a much wider multi-elemental response. And to do that, we use a pulse glow discharge. But first, it's probably a good idea to kind of consider why we couldn't just use a typical glow discharge to achieve that kind of a system. So hopefully one of these pointers is going to work. Here we go. Okay, so in a typical glow discharge, it's operated continuously, of course, sampled by sputtering. So the power is applied continuously as a function of time. Let's say we had a solid surface that maybe had some morphology to it. Here are a bunch of yellow-colored atoms that are on a base of red-colored atoms. And of course, continuously what's happening is the glow discharge is struck between the anode, which is the vacuum chamber, and of course this is at about 1/4 of an argon environment, and the cathode, which is your sample. And so sputtering then is going to remove material from the sample surface, and it's going to be sputtered out into the negative flow of the glow discharge, where it'll be excited, and then we'll detect it by atomic emission spectroscopy. But you think about the problem here, in getting lateral spatial resolution, and it has everything to do with diffusion. As those atoms move from the surface, they bounce along within the negative glow, they're excited multiple times, and so what you get, if you were to look at the selected wavelength of the emission for your yellow atoms here, what you get is a big blob. So there's very little spatial resolution. So the result, of course, is poor lateral spatial resolution. But if you were to think about doing this with a pulse flow discharge, you can solve the problem pretty simply, right? You simply, now we have a pulse power waveform, so typically it's off, and then we turn it on, the glow discharge forms, and immediately we start to sputter away material from the surface here in the same way that we did before. But now, because the plasma has a short lifetime, that means that there's not a large distance that the atom can move from its origin into the negative glow before it's finally excited and emits. And so what we do then is simply excite those atoms that have moved directly from the sample surface and are excited by the negative glow, and turn the discharge off. And the only thing that remains are the ones that moved a small distance from their origin. And therefore we get this high spatial resolution, high on the order of, say, 1 millimeter to 100 microns. Now to do that, you need some means of doing some spatially selective, wavelength sensitive or selective spectroscopy. And we do it by using something that we call monochromatic imaging spectrophotometer. It's basically just the same type of instrumentation system that you typically use, but we modify it, we tweak it in just a slight way. So here's a very typical glow discharge cell, I guess, again, in a reduced pressure of argon as the environment. We image, or we collect the emission from the sample cathode, which sits here, but instead of placing the lens at 2F, we place it at F. And that means the light that comes from the sample surface is not focused onto the slit of the monochromator, it's collimated. So the collimated light then moves into a monochromator, and here we use this as our wavelength selection device. So we choose a wavelength of interest by changing the slit width and the grading angle, and then we use a focusing element here to reconstruct the image on the surface of an ICCD. And the object then is that we can choose a wavelength of interest and simply get a spatial profile. Now, it works fairly well. This is a comparison of our continuous type of model with what we would achieve with a pulsed source. So what we did was we took a sputtering crater here. This happens to be a PVDF membrane, which will become important here in just a moment. It's an insulating material onto which we put 2 little dot spots of silver nanoparticles. And we imaged it using either continuous excitation or pulse excitation. And as we said before, under continuous excitation, all the diffusion simply smears out the emission profile here at the excitation of silver atom at 3280 angstroms. If you apply the pulsed waveform using a short lifetime, here on the order of 200 microseconds, we're using radio frequency because this is an insulating sample, you can see that we maintain that spatial resolution, which is what the key to what we're trying to achieve here. The reason that I chose this particular example, and it's an insulator, and it's something called PVDF, is that we have a really specific application in mind. That is, we want to do atomic imaging of gel electrophoretic separations, with the idea that we could take something from biochemistry that bioinorganic chemists do all the time, do these gel separations. And we could say, well, it happens to be iron in these particular spots, and then we excise those spots and then work them up by other methodologies. With the advantage that we can be very quantitative and we get multi-elemental response. So as I said before, the separation technique here is gel electrophoresis, which I'm sure many of you are familiar with. We do a 2-dimensional separation along molecular weight along one axis and isoelectric point along the other. And really the point I want to make here is that the result is a 2-dimensional kind of grid of biopolymers, which have been separated into dots that are on the spatial segments of, say, a millimeter square. And there might be 10 or 100,000 different proteins within that species. The second step that's typically used is to blot that separation onto a secondary surface. In this particular example, I'm using electroblotting. So we just apply an electric field and transverse across our gel electrophoresis membrane. And we take whatever was in the gel material and we put it right onto a secondary material. In this case, it's that PVDF membrane that we talked about before. And it has another advantage. The advantage here is that the proteins are now concentrated on the membrane surface, which means we have a high surface concentration that we can work with. Now, typically what you do is then detect them by some secondary means. Now, we're going to detect them by atomic emission spectroscopy, A number of methods have been used in the past, but there are some advantages, particularly for atomic emission spectroscopy. Many of the metal-containing species here, or the stains that are typically used in bioanalysis, have metals already. So the protocols are actually worked out really well. Further, you can get these metal-containing fluorophores commercially, which are targeted to specific things. If you want to even get more specific, you can think of element-coded affinity tags, or element-containing, maybe tags that have some special isotope or element that's not normally found in biological systems. So you can use the antibody type of specificity to gain some more information. And finally, you can think of using the constituent elements themselves, such as phosphorus, sulfur, carbon, so you can do interesting things like carbon-sulfur ratios directly from these types of analysis. So with that as the end goal, I'll give you some preliminary results. This is a dot plot methodology that was typically used for quantitating proteins. This happens to be BSA by 5.8 millimeter diameter here. This is using a silver stain in order to visualize these species. And the idea here is to see how quantitative we can get in terms of increasing the detection limit and get proportional response. So these different values dictate the concentration of protein that was laid down on the membrane. We silver stain them, and then we look at atomic emission at the silver stain material. What you see here is that you see higher emission, of course, at the higher protein concentration. Here at the lowest concentration, if you do a quick back of the envelope type of calculation, for 1 square millimeter spot, you'd get a limit detection that's about 2 femtomoles of BSA, which actually is fairly good for a fairly simple method. We'll compare that here in just a moment. Here is a standard protein mixture that was separated now in a one-dimensional gel electrophoreograph, and we blobbed it using the mechanism that I talked about before, and we imaged it. First, this is a photograph of exactly what the blob material looks like. The thing that you note is that there's a different, say, sensitivity for the amount of silver that's actually attached to each one of these proteins by non-covalent bonds. And that's kind of a problem with quantitating by this methodology. But you see, if you place it into this type of system, you can get proportional response. This happens to be a photo of what the section will be excised, and then if we do the low discharge atomic emission spectroscopy, you can see that you see silver emission at the correct wavelength. In terms of the detection limits that we can achieve by this methodology, here we compare them with a number of different total protein stains typically used in biochemistry. These, in many cases, are what typically used in wet chemistry laboratories. We're down here at about 0.05 nanograms is our minimum detectable quantity. Now this is using silver staining, which is as the de facto methodology used in a lot of biochemistry labs. But we have the added advantage that we can actually think about looking for particular elements that are within a protein of interest. So this is an example in which we've taken myoglobin, we placed it on a glass background in this particular method, and we've detected various concentrations in order to show that in fact we can get one, a linear response with a large order of magnitude. This happens to be 3 orders of magnitude. And 2, that we get very good detection quantitation based on the stoichiometry of the protein metal complex. So here we get about 0.21 nanograms of iron as the detectable quantity, which is about 62 nanograms of protein. So this kind of methodology should have a lot of interest for people who want to do discovery, what we might call discovery metallomics, where you'd have a biological system, you don't know exactly kind of the metal content that you want to look for, but you're just prospecting. So you could do a 2-dimensional separation, place it to an instrument like this, and get valuable information. There are a number of other applications for this imaging technology that we're looking at. Now I want to switch gears a little bit and talk about the direct analysis of liquids. And we do this by a slightly different type of glow discharge. It's known what we call a solution cathode glow discharge. And it's a glow discharge plasma that's sustained directly on a liquid surface. The idea being that we don't need an ICP OES type of instrument. Maybe what we could do is create a glow discharge that would fulfill many of the same functions and that we might be able to take into the field. So if you look at all the possible interesting applications you could think about doing, well, it's a very simple type of glow discharge system. It has low cost, power on the typical, somewhere around about 100 watts, like a light bulb. It operates in the open atmosphere, and there are no compressed gases that are required. So you can think about field portable